Hi, and welcome back to Book Club. And we're in Thermodynamics, Chapter 8. Yep, I did skip Chapter 7. So, Chapter 7 in Moran Shaipro, it's on exergy. And honestly, I call it optional rating. Honestly, it's not something that we use a ton of industry unless you're very a particular industry. And it's effectively reframing. We've sort of seen there's a limit of thermodynamics. Like you can only get so much energy out of a system because of entropy, because of realities of life, heat rejection. And exergy is almost just a renormalization if you're a physicist. It's a renormalization of all that such that, zero as you've extracted all you can, rather than having this number that's not zero. That you have to then remind yourself, like, no, I did all I could. I've never found it useful. I've had to teach it before. I have no intention of teaching it here. And so we're going to jump to Chapter 8 because this is the fun stuff. Okay, this is ultimately Chapter 8. It's like cycles. So like, just look at the beauty of, this is a combined cycle. You got LNG, and then there's a tank that you're putting into, and there's some pumps. And if it's cryogenic, then there's a vaporization stack to turn this into a gas. And then you got a gas, and then, you got to be pulling air in, although there's air coming in the system. And then you're burning it. What are you boiling? Well, you're boiling water. And so here's your water loop, and then this is now steam. And then, there's gas turbine is burning from the LNG. This is the steam that is then driving a secondary turbine. I mean, this is like the fun stuff of what you can do. And all this is ultimately then driving a generator. So you got a LNG powered gas turbine with, air is going in this way. So this is the exhaust, which is then, generating steam. So these exhaust heat's generating steam, driving a secondary turbine, driving a generator, which is then making power. And all of this then has also the feed water, whether it's seawater, circulation pump. Anyways, like the realities of a real power plant become just awesome. And thermodynamics to me was fun because like you get into this stuff, okay? And so what we're doing in most of thermodynamics, you would call it still just kind of zero state. It's still just first order modeling. Like that's why I like sort of teaching this as thermofluids, combination of kind of fluid mechanics and thermo. It's because when you see sort of these thermodynamic simplifications and then we just say there's inefficiencies, well, you have an idea of where those inefficiencies are coming from because we're sort of co-teaching this with fluid mechanics, and you can look at, there's going to be drag and viscous losses in those pipes. The flow over the gas turbine is going to be at some weird angles of attack, and there's going to be losses. So anyways, this is why I do it. In sort of this order. And so we're going to start off with the Rankine cycle. Okay? And this is ultimately just steam. Steam cycle. Okay? And it's pretty useful and even a little simplified diagram, so it won't be quite as complicated as what I just flashed up there. Okay? But if you've got some system and you got a boiler, and so there's some combustion happening here. This is your sort of Q in. And then this is now steam, and that steam is coming out, and then you have sort of a turbine here, okay? And this is your work turbine coming out, and then that steam is going to come down to a condenser. There you go. You might have some loop, whether it's air or water. This is pulling your Q out. And then ultimately, you then have some sort of pump going back in. So that's kind of the most basic version behind all of that. Okay, let's label this. So this is boiler. This is turbine. This is condenser. And this is pump. And then from states, I usually think this is state 1. 2 is past the pump. 3 is after you've added the heat. And then 4 is after you've taken the power out. So on a TS diagram, then this is going to look like this, and it'll overlap the dome here. So there's your steam dome, right? So on this side your liquid water, this side your steam, and then I'll do in green. So you may come from here pressurized, so this is 1 to 2, and then boil at high pressure. And then usually what happens is you kind of continue up in pressure to a superheat, such that you reject, go across the turbine. So that would be state 3, and there's 4. And so really, we draw this as just a very simple squiggly line, but in practice, there's actually a couple different things you do to sort of make sure the water is fully dry, and then you sort of hit it again. You bring it back in and hit it again with heat to sort of get up here. Now, why are we doing this? Ultimately, we want the turbine to be gaseous. We want it to be effectively vapor the whole time. If you get liquid, that just turns into like pitting your turbines and just doing a ton of damage. So really, you keep this whole thing in the vapor state. And then your condenser is rejecting all of that heat back out, so you get back to regular water. Okay? And this is usually closed loop, okay? If you wouldn't just say pull river water or pull sea water to do this, all the junk in the water would really damage all of the systems. And so normally this is like deionized or really well taken care of water. Hence why this is not just a dump it back into the river kind of a thing. It is a sort of using a river or using a cooling tower, if you will, to sort of reject the heat. Okay. And so because this is open loop, remember, so if you go back to that, are you going to use internal energy and enthalpy? No, you're going to use enthalpy on these. And so we know that the work of the turbine then is this part. So that would be H3 minus H4. The heat going in is then H3 minus H2. The work of the pump is then H2 minus H1. And then the Q out, so Q in, the rejected heat is then 4 minus 1. And so, if you're going to say, hey, again, the efficiency would be, what are we interested in? Okay, that would be the work, the net work that you got. So you had to do, get work out of the turbine, but then you had to pay a little bit for work of the pump. And then what did you put in? You put in the heat. And so this is then Q in. And so if you do that, turbine, right above, right, so H3 minus H1 minus, and then the pump, H2 minus H1, and then all of that over Qn, which is this H3 minus H2. And if you go, you can reduce that math to 1 minus H1 minus H4 over H3 minus H2. And so to see what that is, that's basically Q out over Qn. All right, so it's sort of not unexpected. All right. I'm going to show you sort of some more advanced ones, which is pretty fun, okay? And then we'll get into some gas versions of the kind of Brayton cycle. And so as you're reading along chapter 8, and again, do some of the problems so you sort of understand, again, how you sort of cycle around, and all these problems are going to be good about, like, you're missing this piece of information, you got to solve for it, or you're given, only given a pressure, you might have to take an isentropic drop and then apply your losses and things like that. So feed water is an interesting one, as well as reheat. So we'll kind of draw this over here. And so a couple different things you can start doing, which really add a ton of value in terms of the full thermodynamic diagram. So let's go say here's 1, 2, same sort of thing, up to 3. But then what you can do, in fact, I'm going to draw it down here, is you do this, you come to a medium pressure, and then you reheat back up to that, and then you come down. So this is reheat. And the nice thing about reheat, if you compare it over here, is look at that, sort of keeping that maximum temperature from getting too high. Because that's going to drive a lot of temperature problems on your turbine. So this is a pretty cool way, okay, to sort of do it. And then the other thing, and I'll draw it in the same diagram because it's not too messy. I don't think it's too messy, but let me tighten this up so it's a little more obvious what I'm talking about. Let's see, because that's going to come back. Here we go. All right. Close enough. I'm going to get this too smudgy. This might represent atmospheric pressure. And so the other thing you could do is then pull down to subatmospheric pressure and sort of extend this way. And I probably should have done that in a different color. But this would be pulling a vacuum on your condenser, right? And so what's going to do is going to shift that down. You're going to get more work out because your turbine can come to a lower pressure, expand it. So you're getting more work out, and you're still able to reject it because this is a closed cycle. And so I actually remember being on board a Navy vessel with the boilers and the, fleet officers were bragging about, like, well, how many inches of vacuum you get your system to, right? They're kind of talking about this because it ultimately, for everything else being constant, if you're able to get pull a vacuum here, you get more efficiency out of it. So, yeah, there's some pretty fun stuff you can do within even just the Rankine cycle. Okay, and then when we go to the gas cycles, I should have enough room here. I'll try not to go too crazy. And so the gas cycles, this would actually be chapter 9. But I'll start here. So the Otto cycle, this is sort of your car engine, okay? And if you draw a little kind of diagram of your piston going, okay, and 4 stages of compression, then if you draw that TS diagram, and I'll even draw a PV diagram because it's sort of the important distinction here of the Otto cycle, is that your combustion effectively is happening at constant volume. So you sort of raise the piston to compress, and then you would draw down to draw in air and mix the fuel. You would compress to here, and then you would add, effectively, your spark goes, it lights your spark, your flame burns, and then you add the heat. Now it's not purely constant volume, but for the most part we can examine it like that. Okay, and then 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Now, in this case, the control volume is set, right? So I'm not going to actually use enthalpies on this one. I'm going to use internal energy because the control volume, I don't have things sort of going in and out. At the end of the cycle, yes, you're rejecting everything and then drawing new things in. But between the states, that's not the case, okay? And so the efficiency then, same sort of thing, it's basically this formula here. And so I'm just going to repeat what it is now for this case. And so it's U3 minus U4. Actually, this one, that's not a 1. Gosh, that's a 4. Yep. Okay. Minus the work you had to put in, U2 minus U1, and then over the heat that you added. So it's basically the same thing as this below, and this becomes U1 minus U4 over U3 minus U2. Okay, well, because air it does decently with an ideal gas, okay, you can actually then say, well, for one, let's just use constant volume specific heat, so that internal energy, right, is just related to temperature. And then, honestly, ideal gas relations are going to set that T2 over T1 is going to be equal to just the change in volume, V2 over V1, raised to the gamma minus 1. Or we will call that the compression ratio, the gamma minus 1. Okay? And so if you come back to this efficiency, and I'll let you see sort of the rest of the math in the chapter, but basically the efficiency comes down to 1 over that compression ratio R to the gamma minus 1. And so this is why a lot of times, car engines, to the first order, the performance of the car engine is basically just, hey, what's your compression ratio? Okay, what's your compression ratio? We're going to see in the Brayton cycle, the same thing is going to be true of a jet engine, which is basically your efficiency is like, hey, what's your pressure ratio? Okay, so compression ratio here is what's driving it. Okay. And then I'll draw a diesel here, and I should have enough room to finish with Brayton. And you get like kind of the full spectrum. Okay, so diesel is a little bit different. In fact, I'll just draw sort of the PV diagram. Okay, because what's happening in a diesel cycle, 1, 2, 3, 4, is this right here. It's constant pressure heat addition. And some of it is just due to sort of diesel auto ignite. So here it's a spark, and so your flame front goes crazy. Here, it's sort of an auto ignition, and it's a little slower process. So as your car engine's kind of going up and down, it looks more like a constant pressure point of view. Okay. And so because it's constant pressure, this is then one of those weird ones where is it internal energy? Is it enthalpy? And so you got to be careful with the math. You can do the reading, okay? But ultimately, you will see that it's sort of this mixed one. So this is U4 minus U1 over H3 minus H2. And again, that goes back into the definition of enthalpy and why you would use that state. Otherwise, you have to account for that pressure work there. Okay. And so that one's still, it's still going to be sort of related to the compression ratio, but then you also have sort of the ratio here of the, how long is that combustion occurring across however many crank angles. So if you're a car nut, this is sort of just the very beginning, and you could do a couple different problems with this on all this different stuff. Okay, and then I'm going to finish with the gas turbine. Okay, and so the gas turbine, you can sort of model it. We usually model it in these blocks, and it's sort of silly. That's not how a gas turbine's made, but it's how we're going to model it. Okay, air is going to come in. Okay, this is state 1. And then it's going to get compressed. So you can imagine this is just rows of compressor blades that are going to compress the air. And that's state 2. And then our combustor is going to mix fuel in that combustion process and then add heat. And so that's state 3. And then we're going to take that high pressure, now high temperature, expand it over these turbine blades down to state 4, and then we're going to exhaust that out to the atmosphere. And there's sort of this implied closed loop, if you will. Now, it's not fully, because your exhaust goes that way with all of the sort of exhaust products, and what you're drawing in here is fresh air. But even most times in thermodynamic cycles, you're not even going to consider the constituents here of the fact that there's now water and CO2 in the exhaust and things like that. Like really kind of the first order, you would ignore that. Okay, and so then the efficiency here, and it's literally the same formula. That's why it's fun to kind of do this all on one screen. It's the same formula, but this time it is enthalpies. Okay, and so it's basically the same formula there. In fact, I'm just going to say, like, if I could draw a big arrow, maybe that would be too crazy. Right, over H3 minus H2. But the difference, though, honestly, the difference is not on a TS diagram. I'll draw it here. Okay, TS. It's a constant pressure heat addition. So 1, 2, 3, 4. And these are all lines of constant pressure. And so there's not a dome here, right? So Rankine's is a vapor dome. There's no vapor dome. This is basically just air. And so your Brayton cycle is doing that, okay? And then combined cycle was actually that crazy one that I flashed up earlier, where you would then take state 4 here, and then you would use that to be your boiler here. And that's combined cycle. And so you get sort of this double system. It's pretty awesome. And then the other one you might hear about is combined heat and power. And so that's either saying, hey, I'm going to take state 4, which is hot, and that can be here, or honestly, it can be some portion here. And so they have this a lot at the universities, where you have a power generation system, and then the exhaust or the hot steam is then actually run around campus in these pipes and heats up all the buildings. So that's sort of combined heat and power. And honestly, like that's where it wins. So like that jumps, so almost all of these efficiencies just generically are going to be in the 30%. But when you account for the fact that you actually use your waste heat for some other purpose, that effectively gets your efficiencies up into the 60s and 70s. And so honestly, as people are concerned about power generation and carbon production, one of the things we really should think about doing is, where we can, like at those universities, you really should use the waste heat from your power generation system to provide heating. Okay, you shouldn't necessarily have a separate furnace in each building that's burning propane or burning natural gas or electrical heating, whatever it is in each building. You should be using the exhaust products of the power that you're generating. And so that's that cogeneration plan. And that's a massive jump up in terms of efficiency. And so for sure, you can think of like downtown buildings or big campuses, probably not practical on like a housing neighborhood, things like that. But really, there's a lot that can be done. Okay, and then in terms of gas turbine, go see sort of the high-speed flight series that I talked through this on gas turbines, or go see the book club #1, where I do a little bit more details on gas turbines. And then ultimately, I am going to do sort of I believe the next book club, I'm actually going to go dig into propulsion systems in general. So there'll be a rocket book and then a gas turbine book. So I'll come back to this for sure in that book club. So that's cycles. And this is why I love this stuff. That's why, people, when I first took thermodynamics, people said they're always kind of scared or they always had a bad rap. But I was just fascinated. It's like, this is power generation. This is propulsion systems. This is phenomenal. So I hopefully enjoyed it. Again, if you like the book club series, like and subscribe, and we'll see you next time.